morning students, welcome back to your chemistry class. So in continuation to the yesterday's video, the previous videos, yesterday we were doing the merits of the Bohr's atomic model and I couldn't complete because of the video, right? So the last point, the last merit was left, that was the explanation of hydrogen spectra, right? So the only electron in the hydrogen atom, it resides under ordinary conditions where? On the first orbit. We all know this. Now, when energy is supplied, what will happen to the electron? When the energy is supplied, it will move from lower energy shell to the higher energy shell, depending upon the amount of energy that it is going to absorb, right? When this electron, it returns to any of the lower energy shell, then it will always emit energy. All this I had explained you yesterday. Now look at all these series. I have drawn it for you from beforehand. Look at the Lyman series first and foremost. It is formed when the electron, it returns to the lowest. Now I have marked it over here, K, L, M, N, O, P. So which is the lowest orbit? K is the lowest orbit. So the Lyman series, when is this formed? It is formed when the electron, it returns to the lowest energy state. Okay, see, from here to here it will move, or from this energy state to the lowest, any of this to the lowest energy state, then it is forming a Lyman series. Right now, when is the Balmer series formed? Balmer series is formed when the electron, it returns to the second energy shell. Look at the second energy shell. L is the second energy shell. So when the electron, it returns to the second energy shell, N2, then it is always going to form a Balmer series. Similarly, now look at the Paschen series. It is going to return to which one? It will return to the first, second, third one. Okay, third energy shell. When the electron returns to the third energy shell, then it is always going to form which series? Paschen series. When it is going to return to the fourth one, that is 1, 2, 3, fourth energy shell. When the electron returns to the fourth energy shell, it will always form a bracket series. And the Fund series will be formed when it returns to which one? 1, 2, 3, 4, fifth energy shell. When the electron from the last shell moves back to the fifth energy shell, then it forms the Fund series. I hope this is very clear to you. So, the maximum number of lines, where are they formed? When an electron, it jumps from the nth level to the ground level, and this will always be equal to what? N minus 1 upon 2, right? For example, look at the case where n is equal to 4, right? Now, how many number of lines will be produced? How many number of lines will be produced? 6 number of lines will be produced. How? Look over here. And let me write it down over here. If n is equal to 4, then number of lines produced will be 6. Now how? Let me explain you. Look at that. I'm writing it down and you correlate it with the figure over there. So when the orbit number is 4, 4 to 3, this is the first line that you are going to see. Then the next one you will see 4 to 2. Okay. Then the next one will be 4 to the first shell. Then 3 from third shell, it will go to the second one. Then from the third shell, electron will go to the first shell, and then from the second shell also it will move to the first shell. So how many? 1, 2, 3, 4, 5, 6. What did we see? That if the electron has to jump from the fourth orbit, then how many lines will be produced? 6 lines will be produced. If the electron comes back from the energy level having energy E2 to the energy level, say it goes to E1, then what will be the difference that will be created? It will always be delta E. The total energy difference will be how much? Delta E, which can be written like this: E2 minus E1 is equal to delta E. And we also know that the difference can also be expressed in terms of energy of photon. So this can be equal to H frequency, or this is called as Planck's constant into frequency. So how can we write down what is frequency then? Then frequency will be equal to delta E upon Planck's constant, right? So delta E, they have only definite values depending upon the definite energies of your E2 and your E1, right? And the frequency will also have only fixed values in an atom. Thus, I can say, I'm writing it down over here, that frequency is equal to C upon lambda. This will be equal to what? Delta E upon Planck's constant. Therefore, this is equal to how much? Hc upon delta E. Now since H we know and C we know, they are constants. Therefore your delta E, it corresponds to what? To the definite energy. Is that clear? I hope this much is very clear. So each transition from one energy level to another energy level, it is going to produce light of certain wavelength. Now this actually was observed as a line of spectrum in the hydrogen atom. Thus the different spectral lines in the spectra of the atoms, it corresponded to different transitions of electrons from higher energy level to the low energy level, right? So now I'm going to explain it to you with the help of the derivation. So I'm rubbing this. I hope this much is clear. So with the derivation, I will explain you now. So as I told you, the different spectral lines in the spectra of the atoms, they correspond to different transitions of electrons. That is from the higher energy level to the low energy level. So suppose I say let N1 and N2 be the two energy shells in the hydrogen atom, right? Where we are going to observe that N1 is a lower energy shell and N2 is the higher energy shell. Clear? Now, energy associated with N1 shell. How much? This I had explained you yesterday. The formula, if you remember, 2 pi square Me4 K2. K was the constant, if you remember. Then N1 square H square. Okay. And similarly, energy associated with N2 shell. This will be how much? This is also 2 pi square Me4 K2 upon N2 whole square H whole square. Now, En2 minus En1, that was delta E, right? Let us do this. This is En2, sorry, this is En1, this is En2. So what have we to do? We are going to subtract the two. Okay, so let me write down over here. En2 minus En1. This will be equal to how much? Sorry, here I forgot to write down minus. Okay, so let us write minus 2 pi square Me4 K2 upon N2 whole square H square minus 2 pi square Me4 K2 upon N1 whole N1 square and H square. Till here I hope everything is clear. Now let us solve this equation. Okay, so what is E2 minus E1? That is delta E. Just now I wrote it down. So delta E will be equal to what? Let us take the common things outside. 2 pi square Me4 K2. This is common upon H2 is common. What is uncommon? 1 upon N 1 square minus 1 upon N2 square. Okay, right? So delta E will be equal to what? Fine. This is equal to what? H. What is your frequency? C upon lambda. So H C upon lambda is equal to what? Let's write down 2 pi square Me4 K2 upon H2 1 upon N1 2 minus 1 upon N2 2. Till here it's clear? I come over here now. So 1 upon lambda will be equal to then how much? 1 upon lambda will be how much? 2 pi square Me4 K2 upon HQC. H square into H makes it HQ into C over here. 1 upon N1 square minus 1 upon N2 square. Right? So 1 upon lambda will be then equal to what? As V with a vector sign over it, and this is also equal to RH. Now you must be wondering what is RH. RH is the Rydberg's constant. I'll write it down over here. RH means Rydberg constant. Okay, for hydrogen, and its value is also specified given in the question, that is 109677.76 per centimeter. Of I can write it down like this. Okay, this part you need to remember what I have written over here. Okay, 1 upon N1 2 minus 1 upon N2 2. Fine. Now this is also termed as wave number. Here, what is this? This is called as wave number, which is written with a vector sign or a dash on top. Okay. So over here we can write this is equal to RH into C 1 upon N1 square minus 1 upon N2 square. So this is your final formula that is formed when we need to calculate the wave number. Okay. Now for Balmer series, now remember that for Balmer series, always your N1 is equal to 2. Go and check the diagram that I had drawn. Then and for N2 it will be 3, 4, 5, 6 and so on. Okay, these are the values for the Balmer series. For N1 it will always be 2, and for N2 it can be any of these. This will be given in the question. So I hope the explanation of hydrogen spectrum is clear to you. Now, some of the more points that supports Bohr's theory are that the frequencies of the spectral lines, they can be calculated from the Bohr's equation, and they are close with agreement with the frequencies that are observed experimentally in the hydrogen atom. Then even the value of this Rydberg constant for hydrogen is, which was calculated by Bohr's equation, it tallies with the derived experimentation. Okay, and the emission and the absorption and the spectra of the hydrogen, all these species which have one electron, that is helium ion or your lithium ion, right, they can be explained with the help of the Bohr's theory. So this was all your Bohr's theory. Now let us come to the limitations of the Bohr's model. So I'll mention over here the limitations of the Bohr's model. Next we come to limitations of Bohr's atomic model. Now, the first point, it does not explain the spectra of the multi-electron atoms as we have been discussing. It only explains about the hydrogen atom which has one electron. It does not explain the spectra of the multi-electron atoms. Okay. So, first point, it does not explain the spectra of multi-electron atoms. Second point, when a high resolving power spectroscope is used, it is observed that spectral lines in the hydrogen spectra is not only a simple line, but there should be collection of lines which are very close to one another. So this is known as the fine spectra. But Bohr's theory, it does not explain that fine spectra of for even the hydrogen atom, because there is no continuous lines. One line is formed, then after several distance another line is formed, then after several distance another line is formed. The continuous spectra is not formed even in the hydrogen atom. So his model was not able to explain that fine spectrum or the continuous spectrum. Okay, his theory could not explain the fine spectrum, or what we call as continuous spectrum, even in the hydrogen atom. Okay. Then the third point, he did not explain the splitting of the spectral lines also into group of finer lines under the influence of magnetic field, which is also called as Zeeman effect. And he could also not explain the electric field, that is also termed as the Stark effect. Okay, did not explain the splitting of spectral lines into a group of finer lines under the influence of magnetic field. And what is this effect called as? This is called as Zeeman effect. Okay, and under electric field, then it will be called as Stark effect. His theory could not explain these two. Then the fourth point, he did not he was then Bohr's theory is not in agreement with the de Broglie's concept of the dual character of the matter that we will be teaching, which I will be teaching next. Okay, so Bohr's theory is not in agreement with de Broglie's concept of dual character. Okay, then it also did not support Heisenberg's uncertainty principle also. Then it did not explain the three-dimensional model of the atom. Did not explain the three-dimensional model of an atom. And lastly, it did not explain the shape of the molecules also. Did not explain the shape of the molecules. So these were some of the limitations, or we may say the weaknesses of the Bohr's model. I hope this much is very clear to you. Now, there are certain questions based on the formulas that we have done in Bohr's atomic model, which I am going to talk about now. To the numericals. Okay. Look at the first numerical. I am writing down the question also. Calculate the radius of Bohr's third orbit in lithium. What is the ion over here? 2 plus ion. So how are we going to solve this question? Calculate the radius of the Bohr's third orbit in the lithium ion. So we know that the radius formula is equal to what? N square upon Z into 0.529 Armstrong. This is what we had studied yesterday. And when N is equal to 3, then atomic number is also 3, that of lithium, right? So our radius of the third orbit, it is talking about radius of the third orbit, this will be equal to what? N square. N will be 3 square upon what is the value of Z? 3 into 0.529 Armstrong. Clear? So when you calculate this, what do you get? 3 gets cancelled. So this comes out to be 3 into 0.529 Armstrong, which is approximately equal to say 1.587 Armstrong. Is that clear how to do this question? Then moving to the next question. Now let us look at the second question. It says, say the ionization energy of hydrogen atom is 13.6 electron volts. What will be the ionization energy of helium and lithium ions? Okay, this is the question. It says the ionization energy of hydrogen atom is this much. What will be the ionization energy of helium and lithium ions, right? So let me write down solution over here. How do we solve this question? So ionization energy, it is equal to what? Minus energy of the first orbit. Clear? Then what is the energy of the first orbit? This is equal to, it's given, minus 13.6 electron volt. Now energy of the first orbit of helium ion, this will be equal to how much? Minus 13.6 into Z square. Now what is Z? Z is the atomic number of helium. What is the atomic number of helium? 2. So this will be equal to minus 13.6 into 2 2s are 4. I hope that is very clear to you. I'll write it down over here. Z for helium ion is 2. So Z square becomes 4. So when you multiply this, it becomes what? 54 minus 54.4 electron volt. So the ionization energy for thus ionization energy of helium ion will be equal to what? Minus 54.4, which is equal to plus 54.4 electron volt. This is your answer. I hope this is very clear to you. See, I have already mentioned over here, right? The ionization energy is equal to minus to energy of the first orbit. So we first found out the energy of the first orbit is this. So minus energy of the first orbit, minus becomes plus. Now let's do the energy of first orbit of lithium, 2 plus. Now this is equal to how much? Say it's minus how much? 13.6 into, now lithium, Z for lithium 2 plus is how much? 3. So this is 3 is a 9. Okay, so this will become how much? Minus 122.4 electron volt. Therefore ionization energy of lithium 2 plus will be equal to what? Minus 122.4. This is equal to plus 122.4 electron volt. I hope it is very clear to you. Coming to another question. Let's look at the third numerical. It says, the question says, the wavelength of a certain line in Balmer series is observed to be 4341 Armstrong. Okay, to what value of n does this correspond? Where it gives RH is equal to, do you remember the value of it? It is 109678 per centimeter. So now, how are we going to solve this? It says, again, the wavelength of a certain line in Balmer series is observed to be this much. So what value of n does this correspond? So write down the formula first and foremost. These are all formula based questions. Okay, so 1 upon lambda is equal to RH, 1 upon n, sorry, this will be Balmer series. It starts from which orbit? Second orbit. So 1 upon 2 square minus 1 upon n square. Okay, so if you solve this, it becomes what? Uh, 1 upon lambda into RH is equal to 1 upon 4 minus 1 upon n square. Okay, when I open the bracket, now, fine. So I make this 1 upon n square will be equal to what? 1 upon 4 minus 1 upon lambda into RH. This is the formula that I've got. Now just have to place the values over here. So this is equal to 1 upon 4 minus 1 upon. Now what is the value of lambda? It is already given to you there in the question, 4341. Now it is given in Armstrong. Okay, I have to change it into centimeter. If you remember, then it should be multiplied with 8 into RH. What is the value? Because it is in centimeters, so I took it in centimeters, into what is the value of this? 109,678. Okay, so when you calculate, all this will come out to be approximately 0.04, right? So n square is equal to 1 upon 0.04, isn't it? When 1 upon n square is 0.04, so n square will become 1 upon 0.04, okay, which is also equal to 25. Therefore, n is equal to what? 5. This is what it is asking. What value of n does this correspond? So it corresponds to which orbit? To the 5th orbit. Okay, with this I wind up today. Thank you.